I had planned to discuss some of the aspects of statistical mechanics, where I would like to confine to two topics, that is microstate and macrostates. So, statistical mechanics is made of two words. Statistical, we mean our approach is based on probability, and mechanics, we mean we are dealing with huge number of particles, and number of particles that is comparable to Avogadro number. So, we are familiar with Newton's equation of motion, where we can solve equation of motion using certain approach defined by Newtonian mechanics. Since number of particles that is used, it is comparable to Avogadro number, therefore, solving Newton's equation of motion for 10 power 23 number of particles is impossible, even with the available supercomputers. So, we are not in a position to solve equation of motion, that is Newton's equation of motion for 10 power 23 particles. So, we rely to another method that is accessible to us through statistical mechanics. In this mechanics, what we do? We approach theory of probability or method of probability to define position, or rather to say distribution of molecules which is huge in numbers, that is 10 power 23 number of molecules are having certain distribution at any instant, say t. Since these molecules are tiny particles, they bear very small mass, so they quickly switch their position. Therefore, we should have idea of these molecules at every instant with the help of theory of probability. To continue along this line, we have an ideal gas which is defined using three thermodynamical parameters, say capital N, capital V and capital E. So, this capital N defines number of molecules which constitutes the gas, V is the volume of container in which this gas is kept, and capital E is the total energy of molecule which is shared by capital N number of molecules, and capital N is comparable to 10 power 23. So, N, V, E, these three parameters are macroscopic parameters. So, these parameters N, V, E, they are similar to temperature. Say temperature you can measure directly using thermometer. So, it is a macroscopic parameter. Now, this ideal gas consists of n number of molecules, and molecules are non-interacting. Therefore, we can write two equations. Equation number 1, that is written for total number of molecules, that is capital M, where I index is used for energy state of the molecule. So, energy state, say first energy state, second energy state, third energy state, and similarly we have say 10 power 23 energy states. So, this first energy state which is labeled by energy value epsilon 1, second energy state that is epsilon 2, similarly third energy state is labeled by energy value epsilon 3 and so on. So, these are the energy value for individual molecule which is in the energy state say 1. So, if one molecule is there, energy is epsilon 1, if two molecule is there, 2 into epsilon 1, if three molecule is there, 3 into epsilon 1. Similarly, energy state 2 which has energy value epsilon 2, one molecule is there, epsilon 2, if there are two molecules in this energy state, so you have 2 into epsilon 2 and so on. So, this say n1 number of molecule is in energy state epsilon 1, n2 number of molecule in epsilon 2, n3 number of molecule in a third energy state which is defined energy to have energy value epsilon 3 and so on. So, we have sum of these molecules, that is capital N, and total energy that is distributed among these capital N number of molecule is capital E. So, this is the total energy which we can write in the case of ideal gas molecule or molecule which are non-interacting. So, at any instant we have certain distribution of molecule among these energy state which is starting from 1 to say 10 power 23. So, one of the possibility of a distribution at any instant t which satisfies equation number 1 as well as 2 is a microstate. Similarly, at later time, say 10 minus 8 seconds later, molecules redistribute among different energy states. So, you have another possible distribution, that is N1 dash, N2 dash, N3 dash, and so on. So, this another microstate further satisfies both the equation number 1 as well as 2. So, this is another microstate and so on. You have possible microstates where molecules are switching from one to another state. So, it will lead to have possible distribution at any instant. So, at one instant, another later instant, this distribution and so on. So, at each instant, each of the microstate is required to satisfy equation number 1 and equation number 2. So, number of possible microstate for 23 molecules is huge, and this total number of microstates are defined using symbol omega. So, any system which is left to itself would like to maximize number of microstates. Okay, number of this. So, this is the natural tendency of any system, or this is principle of statistical mechanics, where system which is left to itself, it would like to maximize number of microstates. So, maximum number of microstates we mean we are in the equilibrium state. So, equilibrium state is a state where system has accessible number of microstates which is maximum, or system would like to spend its maximum time. So, this talk describes you what we mean by statistical mechanics, what is microstate and what is term macrostate.